Yeah, and then there's more utilization, not the page. Sketchup utilization onto the page. No. Okay, let me just do this. And then, so now we're going to find the gradient in coordinates. So the gradient differs depending on the coordinate system. So spherical coordinate system or coordinate system, the coordinate spheric. Okay, so the first step, you always do the same thing for everything. You just have to know the unit vectors or the base vectors of that spherical coordinate system. So which is ER, E theta, then E phi. Okay, that's the first step. The second step, identify which ones are angles. So we've got theta and phi as the angles. So say tell us, what is theta associated with? Theta is associated with the radius r. Phi is associated with the radius rho. But since this is a spherical coordinate system, rho is not there in the spherical coordinate system. We have an expression of rho. When you watch my videos on the coordinate system, you find that rho was expressed to be r sine theta always. Okay, so once you do this, then it can help you with knowing the expression of nabla. So you say gradient of f is nabla of f. So what is nabla in the spherical coordinate system? So nabla would change depending on the spherical. So you say er is a unit vector in the direction of r. So this is the radius. Okay, so if you've got the radius, it's not an angle, it's a radius. R is the radius. So you say del over del r. Okay, then the second component, this is theta, this is the angle. So it's important to know the angle associated to it, the radius associated to each angle. So you say del over del theta, of course, but you multiply by the radius so that you've got the arctan. But it's not important to know whether this is the arctan. Okay, but see, this is how you can create nabla in different coordinate systems. Then the last one as well, you just say the angle is phi, so del over del phi. Then the radius is rho, but we don't use rho in the spherical coordinate system. So you give us its equivalence, which is r sine theta. Then you multiply by f. So you just distribute f everywhere. So this is going to be equal to del over del r. Partial derivative, we say del over del r of f in the direction of what? Er, the first one. Then the second one will be the gradient. As I said, gradient is a vector. It converts a scalar function to a vector. Okay, so you should make sure that you have magnitude and direction. Okay, then the second component is del over r del theta in the direction of what? E theta. Okay, then the last component is del over r sine theta del phi in the direction of E phi. So this is how you find, so you're distributing f everywhere. This is how you find the gradient in each coordinate system. Okay, so that's all you need to know about the gradient. Use nabla. Okay, so I'll give an example. Okay, for example, we've been asked to find the gradient of 1 over r. Okay, 1 over r. So therefore we will say our function is Choro, am I audible and visible? And are you following? Reactions if you're following.
Yes, you're audible
And people are following.
and you're visible and are following. Yes.
Okay, shock and behave. So for you to find the gradient, they will specify which coordinate system. Then this gradient is very important in physics. We're going to use this gradient. Okay, we're going to use this gradient a lot. I will tell you why it's important. Okay, so this is a gradient in the spherical coordinate system. If you watch my videos on spherical coordinate system, I've tried to explain the spherical coordinate systems. MO. So this is the r, the radius. Then this is the angle. Some of you heard me saying theta is associated to the radius r. This is how it looks like actually when you go into the spherical coordinate systems. Okay, So for you to find OM in the Cartesian, you will say, we said it's X, E plus Y, G plus Z, K. Watch the coordinate systems. They are the basis, they are the foundation of this. So then in the spherical coordinate system, then ER, for some of you who are wondering where I'm getting ER, the angles, this is where I'm getting it from. So if you want to find OM in the cylindrical coordinate system, you forget about EGK, you use the ER. So you're just going to say OM, I've got the magnitude R and the unit vector ER. So this is how I can express. So as you can see, OM is a long one in the Cartesian coordinate system, but a very short one in the spherical coordinate system, which means that working with the spherical coordinate systems will be easier than working with the Cartesian coordinate system. So that's one advantage of you knowing each coordinate system. Okay, so you know how to find OM in each coordinate system when you watch that video on coordinate system. So I just wanted to remind you where R comes from. Then R is also in 3D. So R is also expressed as the x squared plus y squared plus z squared. Then we've got rho. Rho is here, then phi. For some people wondering where I was saying rho is associated with phi. Then rho is between y and x. Okay, this is part of the coordinate system, or this is part of the coordinate system. So rho is the so by Pythagoras theorem we say rho is like the hypotenuse of this rectangle. Okay, so rho squared is equals to this side and this side. This side which is equal to x squared plus y squared. So rho is also written as x squared plus y squared. Then r, since r is also the hypotenuse but it's in 3D, so you just add you just say x squared plus y squared plus z squared. Okay, so these are the important information that you need in order for you to solve this question. So they'll just tell you find um no, I fasted too. So they'll just ask you this question, simple question. They will not give you enough information. Trouver la gradient de 1 over r en coordonnées cylindriques cartésien et sphérique. Okay, so this exercise is to show you why you have to know how to find the gradient in the spherical coordinate system rather than just knowing the Cartesian coordinate system. You will find that finding the gradient in the Cartesian coordinate system will require a lot of work other than finding the gradient in a spherical coordinate system. So let me show you why. So taking this as an example, so gradient of 1 over r. Okay, so when you look at gradient, you take it as the derivative of 1 over r. Okay, so I'll start with the système de coordonnées cartésien. So we define gradient to be nabla of f. Okay, what is our f here? Our f is equals to 1 over r. Okay, so nabla of f. So nabla of 1 over r, right? Yeah. Now, what is nabla? Okay, nabla in the Cartesian coordinate system is written to be the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. You complete it like this. Okay, so which implies that nabla of f will be, okay, so you just multiply, you just say partial derivative with respect to x of 1 over r. Okay, then partial derivative with respect to y of 1 over r, then partial derivative of z of 1 over r. Okay, now so you have to find each component. This is in the component of e, this is in the component of g, and this is in the component of k. Of course, you're dealing with the Cartesian coordinate systems. Okay, so which means you have to find each component. So we're going to start with the first component. Okay, so we're going to start with the first component, the partial derivative of x with respect to 1 over r, which is the first component. So in Bas Cartesian, you have to express r as a function of x, y, and z because you're working with the Cartesian coordinate system. This is why I gave you the expression of r in the Cartesian coordinate system. It's the radius in 3D. So you apply Pythagoras theorem and you're going to have x squared plus y squared plus z squared, an extension of Pythagoras theorem. Okay? Because you can't find the derivative of 1 over r with respect to x. You've got r. So you convert r. R is a parameter of the spherical coordinate system. So you convert it into the x or y z plane. That is, r is written this in the base Cartesian. Then you can now find the partial derivative with respect to x of a function. So x squared d plus y squared d plus z squared d. This function is the same as the power 1 over 2. Okay, you should follow me nicely. Then this function that you have is a composite function. Okay, so this is a composite function. You've got a function inside another function. What do I mean? If I say u is equals to x squared d plus y squared d plus z squared, so which means that this function is going to be, no, actually the function was 1 over r. Okay, so 1 over, this is your r. Okay, then 1 over r can be written as 1 over r will be written as, if you take this upwards, this is going to be x squared d plus y squared d plus z squared d to the power negative 1 over 2. These are indices that I'm dealing with. Okay, so this is 1 over r, given that your r is this one. And then you're going to, 1 over r is your function, so you're going to say, supposons, okay, u is equal to x squared d plus y squared d plus z squared, right? So your function, your 1 over r will be same as this is u. If you are saying this is u, so you're going to have u to the power negative 1 over 2. Okay, now you know that u is a function of x, right? So the partial derivative with respect to x of u to the power negative 1 over 2, since u is a function of x, what you're going to say is you're going to apply the chain rule. That is, I'm going to show you how do you do it. You find the derivative of the whole function u to the power negative 1 over 2. You're going to apply the power rule. Okay, well, if you have to add that you drop 1 over 2 down the power 1, then you subtract minus 1, right? So you're going to have negative 3 over 2 when you subtract. Okay, this is how you apply the function, the composite function, a function inside another function. But you know that u is a function of x squared plus y squared plus z squared. And here you're carrying out the partial derivative with respect to x. So you're taking this, you should watch videos on partial derivatives. You're taking y squared and z squared as constants. Okay, so the partial derivative of u, so you're going to multiply by u prime. That's how we find a derivative of a composite function. We first find the derivative of everything. Make sure the first step is make sure this function was complex. Okay, so you simplify it into one variable. You say this is equal to u. So you're going to have this function. Then this function you can just find this derivative. That is applying the power. We're going to have this. But since u is a function, is another function of the variable that you are actually derivating to, you just say multiply by u prime. Then what does u prime? The derivative of u, which is u prime. What is u prime? U prime is just the derivative. You already have u, so you just find the derivative of u. So how do you find the derivative of u with respect to x? So u prime is nothing other than the derivative of u with respect to x. Okay. So what is the derivative of u with respect to x? So you treat other variables. This is why you're calling it the partial derivative. You treat other variables as constants. So here you're just going to have 2x. Okay, watch videos on partial derivatives, please. So the u prime is 2x. So therefore, my entire derivative will be, okay, negative 1 over 2. Then you can now say, what is your u? My u was x squared plus y squared plus z squared to the power negative 3 over 2. Then I multiply it by u prime, which was 2x. Okay, so I can cancel out this part and this part. So what am I going to have? I'm going to have, this is what I'm going to have. I'm going to have a negative x squared plus y squared plus z squared, okay, to power negative 3 over 2, then multiply by x here. So yeah, so this is what I'm going to have. If I want again, I can now express this as uh, 1 over the root of x squared plus y squared plus z squared to the power 3. Okay, then multiply by x on top, of course, so x. So do you have questions? In general, when you have a function, a complicated function like this one, when you have a function like this one, called a composite function, for example, there's no need for you to even say u is equal to something. When you just see a function like this, just just apply the power rule to everything. That is, just drop negative 1 over 2, you drop it this side, then you subtract, you apply the power rule. Then you just multiply it with the derivative of what is inside. Then what is the derivative of this function? It's just 2x with respect to x, of course. So I'm going to have multiplied by 2x. Then I just used u to show you so that we can do things step by step. Okay, so for the people who didn't understand, we're going to carry out, because what we're trying to do is finding the gradient. So we're going to carry out the second component, which is the partial derivative with respect to y. So we're going to do, yes, we're going to have a similar step. So this is an opportunity for you to understand again. So the second term, so we found the first term. The second term, the derivative of with respect to y. What is our r? 1 over r of 1 over r. Then what is our function, which is 1 over r? We said it was 1 over the root of r is equals to x squared plus y squared plus z squared. So with indices, this can be expressed as x squared. You express it as a power so that you can apply the power rule. This is why I'm doing this. So negative 1 over 2. Okay, then now I'm supposed to find the derivative of this. So I'm supposed to find the derivative of this with respect to y. That is taking other constants as 0. So this is a composite function, right? This is a composite function. Okay, tre facile. Okay, so what you do is you find the derivative of my entire thing. Okay, this is my entire thing. You find the derivative of everything. That is, you apply the power rule where you say you drop negative 1 over 2, you drop the power, you maintain this x squared plus y squared plus z squared. You maintain this, then to the power, then you subtract. You always subtract from the power, right? So when you subtract from the power, you're going to have, when you do the subtraction, you're going to have, that is going to be 3 over 2. Then you don't end here because you ignored this sigma thing. So you just multiply by the derivative of what is inside. So what are you respecting? What the derivative is with respect to what? To the variable y. So which means this is constant, this is constant. Therefore, you just focus on this variable. So the answer is 2y. The derivative of y squared is 2y. So 2y. Okay. So you find that this is what you're going to find without even posing u is equals to something. It just depends on what works for you, but it's much faster. So I can cancel these 2 down and these 2 up. See, these 2 up, down, and these 2 down. So this is going to be negative y. Then I can take, since the power is negative, I can take it down. Then I've got over 2. So which means the root of, if you remember, indices, okay, that is also below the scope of our course. Okay, so then you find this derivative. Okay, we're going to do it again for people who didn't understand, because we have the third element of gradient, which is with respect to z. We're going to carry out the same thing. So we're finding the partial derivative with respect to z of x squared plus y squared plus z squared with respect to negative 1 over 2. Okay, then what do you do? First, you differentiate. When you have a composite function like this, something inside and something outside, you differentiate the outside, where you apply the power, you drop 1 over negative 1 over 2 x squared plus y squared plus z squared to the power what? To the power t. Then you subtract the power that you know. So this is going to give me over 3. Then what? We don't end here. You multiply by the derivative of what is inside. So this time around, you're taking this as a constant, these two as a constant. You're only considering z squared. This is why these are called partial derivatives. You have, this function has got 3 variables, but you're only partially differentiating it with respect to one variable. Okay, so these are constant. For example, x squared plus 2. If you are told to differentiate this, you're going to say it's 2x. You ignore these constants. You take these as constants. So we're going to ignore them. We're only going to consider here. So it's 2z. So what answer am I going to have? The same thing. You're going to find that there's a similar pattern that you're finding. So you're going to find negative x squared d plus y squared d plus z squared negative 3 over 2. Then you multiply by z. So to simplify it, I'm going to say negative x squared plus y squared plus z squared. Okay, the root, then on top I'm going to have negative z, yeah, then to the power 3, then yeah, to the power 3 like this. Okay, this to the power 3. Then you found the different components. So therefore the gradient of 1 over r in Cartesian coordinate system is equal to, we had different components. Okay, the first component gave us negative x. I remember the answers. The power x squared plus y squared plus z squared. So gradient is a vector. People are forgetting this. In my special classes that I have, people are forgetting to put the direction. So in the direction of x, then plus negative y. Okay, so no need for me to put this negative actually. The minus y over, so this to the power 3. Okay, then the second component we found it to be x squared plus y squared plus z squared. Pay attention. This will be your homework. The same question will be your homework because the gradient of 1 over r is very important in physics. In the direction of g, then minus z. This will be your homework. The exact things that I'm doing now will be your homework. Squared plus y squared. When you start writing the homework, please don't come here and copy like step by step. No, watch, understand, and now try to do it. Try to attempt it on your own. S'il vous plaît. Okay, so that you can see your own mistakes. Otherwise, I won't be there. Then in the direction of k, then you found the gradient. Okay, so if they were to ask you, once you find the gradient, this is how you find the gradient in the what? In the base Cartesian, then you are done. But if they were to tell you, okay, once you find the gradient, can you convert it into the spherical coordinate system? Okay, so it's very easy. So the first thing that you need to know is r in the spherical coordinate system is equal to x squared plus y squared plus z squared. Okay, so here you notice that this is r, and this is r. Okay, so you can actually, when you replace, so you're going to have gradient of 1 over r. So from your expressions down, you have r to the power 3. Okay, so you will have negative x, okay, in the direction of e, over r to the power 3 plus y g over r to the power 3, then plus z in the direction of k over r to the power 3. So they were negatives. Okay, then what else are you going to observe? Okay, you're also going to observe that here when I factor out by negative, okay, I'm going to have x in the direction of e plus y in the direction of g plus z in the direction of k. Okay, then over everything over r3. So what is this? This is OM in the base Cartesian. Okay, plus y. This is OM in the base Cartesian. So what is OM in the base cylindric? It's r ER. Okay, so here you can say this is OM, but we're converting everything. So in the base spheric, so this is OM. So what is your OM in spheric? Because you converted what you found. So if I tell you to find in the base Cartesian, you just end it here. Now I'm trying to show you why this will give us the same answer. When you're trying to convert it, you just identify the parameters that are equal. For example, saying r is equal to the root of x squared d plus y squared d plus z squared. then also identifying that this is OM when you simplify. The other things is just mathematics. So this is OM, then OM is R, ER when you watch the coordinate systems over R3. So there's a negative here because there's a negative here. So therefore, this is negative R, ER over R3. You can cancel the R's if you want to. You'll have negative ER over R squared if you cancel the R's. So the answer is this. But if you convert it into base spheric, you're going to have negative ER over R squared, which is going to be the answer when we actually solve that gradient in the base spheric. So that's how you solve questions, and you'll be examined on similar questions. This is an examinable question. Okay, so now you've seen how much we've done just for us to find the gradient in the base Cartesian. That's why we're not advised to work with a base Cartesian, even though it looks simple to work with. For example, you can remember nabla. It's very easy to remember the equation of nabla in the base Cartesian. The equations are very simple, but it requires a lot of work. You need to know how to differentiate the composite function and things like that. This is why they developed the other coordinate systems. If you play, watch my videos on coordinate systems. I repeat, they are very essential. I just don't know why you haven't started learning mechanique du poids yet. But with the people that I've been teaching, we've learned mechanique du poids, and I've overly emphasized on the coordinate systems. They're also going to have an exam on the coordinate, just on the coordinate systems, just to show them it's very important, not just in physics, but also in mechanique du poids. It's like the foundation. So now let's find gradient in system de coordinates spheric. You're going to see that it's going to be shorter than that system de coordinates Cartesian. So the first question is system de coordinates spheric. What do you need to identify? You need to identify the base vectors. If I can remember, I'm not getting this anywhere. If I can remember, it means that you can also remember. Okay, I've got this angle, radius. So this angle is associated with R. This angle is associated with the rho. Then rho in base spheric is R sine theta because we don't use rho. Okay, so what is nabla? So gradient, the general formula of gradient is nabla of the function. Our function is 1 over R. Okay, so now what is nabla in system de coordinates spheric? You look at the first component ER. The first component ER will have, what will the first component have? The partial derivative with respect to R. This is the radius. Okay, the other component is an angle. What did I say if it's an angle? You say the partial derivative with respect to theta, but you add the radius down here. If you look at this factor, radius multiplied by change in theta, this is none other than the arc length. So we convert the angle into an arc length. We find the arc length by multiplying. This is radius, and we've got theta. So we're using this length. So this length is equivalent to r theta. So here we had the change in theta, a smaller change in theta. Of course, the theta means smaller change. Okay, but the only thing that you need to remember when you're writing the formula for nabla in spherical coordinate system is identifying the unit vectors, first step, and identifying what each angle is associated with so that you can put it down here. So for example, the last component is dead over dead phi. Now the question is, what is phi associated with? Rho. But we don't deal with rho in the spherical coordinate system. Please pay attention. So we also need to know the expression of rho in the spherical coordinate system. So it's just instead of saying rho here, you don't put rho. What do you do? You just write r sine theta. Then over f outside. So you cannot distribute your f everywhere according to matrices. So your formula will be gradient of 1 over r will be the partial derivative with respect to r of my 1 over r, okay, in the direction of er, then plus the second component will be the partial derivative with respect to theta. Oh, theta is the second unit vector. So here I'm going to, theta moves with r, so here I'm going to put r. So the direction of e theta, then plus the partial derivative with respect to r sine theta, with respect to if phi moves with rho, and rho in r sine theta is r sine theta. So if then I'm going to, so the function is 1 over r. Okay, so now I'm going to now find each component. I'll start with the first component. What's the derivative of 1 over r? So there's no need for you to convert r into the Cartesian coordinate system where you say r is equals to the square root of x squared plus y squared, because r is the parameter of the spherical coordinate system. So you're already in the spherical coordinate system. So the only thing that you need to know is finding the derivative of 1 over r with respect to r. It's very simple. 1 over r is a quotient, so you apply the quotient rule. So for some of you, if you remember the quotient rule, we said u v prime minus v u prime over v squared. Okay, now you don't need to write this formula, and then all you need to know is whenever you're differentiating, whenever you're applying the quotient rule, this is what you do. You differentiate the first component, which is u. What's the derivative of 1? The derivative of a constant is 0. Then you multiply by the second component, which is r. I'm now teaching you how to always apply the quotient rule, okay, without having to write the formula. Then you subtract. You now find, you do the inverse. You find the derivative of what's down, which is r. What's the derivative of r with respect to r? It's just 1. The derivative of x with respect to x is 1. The derivative of r with respect to r is 1. So 1. Then you multiply by what is on top. Okay. Then over what's down squared, r squared. This is how you apply the quotient rule without having to remember the formula. Okay, then this will give us, this is 0, this is 1.
Can you please repeat?
Okay, thank you. We're finding the derivative of 1 over r, okay, with respect to r, right? Then one thing that we've identified is 1 over r is a quotient, right? Then we all learned in high school the quotient which was you saying u is equals to 1, v is equals to r. Then you apply the quotient rule, which says u v prime minus v u prime. If I remember very well, I think I'm even missed. No, it's v u prime. V u prime, yeah, v u prime, u v prime over v squared, right? But you don't need to remember all this with me. I'm going to teach you how to apply the quotient rule directement. Okay, here's how you do it. You are finding the derivative of this function. What do? You first find the derivative of what's on top. Okay, so what's the derivative of 1? 0. So you say 0. Then you multiply by what's down, r. Then you say minus, you now find you do the inverse. You now find the derivative of what's down. The derivative of r with respect to r is 1. Okay, then you multiply by, you do the inverse. So you are going to multiply by what's on top, which is 1, which is the variable on top, over what's down r squared. Are we on the same page now? The person who asked me to repeat?
Yes. No. How is the r squared? Where does the r squared come from?
So the general formula is u.
Or the v squared?
Yeah, what's down is v. So the general formula is whatever is down, you square it. You square
Alright.
whatever is down. Then you first differentiate what's up. Then you multiply by what's down. Then you now minus, you differentiate what's down, you multiply by what's up, then over what's down squared. So this is, when you simplify this is going to give you negative 1 over r squared. Okay, so you found the first component. Okay, now we're now going to go to the second component. The second component, we said, is the derivative of 1 over r with respect to theta. Then we've got r down here, don't forget. Now, this function 1 over r, doesn't have theta in it. Okay, therefore this is a constant with respect to theta. This is a constant. Okay, so the derivative of a constant is 0. Okay, we're now going to go to the third component, 1 over r, with respect to, it was phi, so r sine theta dead phi. There's no phi in 1 over r, so this is going to be a constant, so this is also going to be 0. So you've seen that working with a spherical coordinate system, the calculations simplify themselves. Not me trying to um, I'm mixing French and English. Yeah. So you notice that the only thing that you had to calculate was the first component, which is this component, because there's r in it. So you found the derivative and you apply the quotient rule as I've taught you. But this part will be 0 and this part will be 0. So therefore my gradient in, you specify which coordinate systems are you using. My gradient is equal to negative 1 over r squared. Okay, then don't forget the direction er, because we just found this gradient is a vector. So people, my students were forgetting were forgetting this. If you forget this, this is not a vector. I'm going to give you half of the points. So this will be your homework. Your homework will be, you find the gradient of 1 over r in both coordinate systems. That is the spherical coordinate system and the coordinate system. So this exercise will help you be familiar with using lambda and also at lambda, using nabla and also using nabla and also knowing nabla in different coordinate systems. If you're good at memorizing, you can just memorize, but with the way I'm teaching you, it's much better. You will see, you can even see from how I'm teaching you that I've understood. Then from understanding, it's even easier for me to remember, to memorize, in short. Okay. Yeah, so that is how you find the gradient. Then gradient is a very important um, the gradient of 1 over r. This is very important in physics. We're going to use it, which gave us so you can also see that we found negative 1 over r squared er. You can also see that even though even in the Cartesian coordinate system, if you convert, when we converted, we had the same answer. Okay, when you convert, so you can either go with the Cartesian coordinate system, which is going to cost you time. Then just identify, just know that r is equals to this in the Cartesian. Then you start now replacing each part. Is going to give you this, or you just remember how to find the gradient in a spherical coordinate system. The other two components will be 0. This component is what is going to give you this, and then you're good to go. Okay, so in general, if I have gradient of 1 over r, okay, gradient is like we're finding a derivative. So this is negative 1 over r squared, then er, that's what we found. Okay, so this can also be represented as negative r over r3 er. Why? Because I just multiply r up and down. It's just the same thing. I can cancel out, but most of the times it's represented by this. So this vector is none other than OM, negative OM over, when O, at the beginning I said O has a magnitude of R, maybe a unit vector of ER, right? So OM will be, so this vector is none other than OM over the module of OM, which is R, the power 3. Okay, so R is the module or the magnitude of OM. Okay, so this is the same as this. So gradient, so whenever I ask you what is the gradient of 1 over the magnitude of OM, you know that the magnitude of OM is R. So you give me this. So whenever you have the vector, in general, whenever you have the vector divided by its magnitude d to the power 3. You know that this is the gradient. This is the gradient. The gradient of this is the gradient of what? The gradient of 1 over OM in general. So this is what you're supposed to know. So whenever you see a vector, for example here, you have a vector RER divided by its magnitude 3. So you know that this is a gradient of 1 over R. So they expect you in physics, we expect you to know without even calculating, because this is why I'm giving you this as an example. And, I'm telling you this is very important, because whenever you have a vector divided by it's the vector 3, that is the gradient of 1 over OM. It's a gradient of something. Okay, you understand why this is important later. So how many minutes is that?
14 minutes.
Okay, 14 minutes. So another parameter that's with gradient. So another parameter that is important. Now, since we've learned how to find nabla in each coordinate system, it's not very easy to so another parameter that is important is divisions. So divisions. So divisions. Now this one is a scalar. So divisions. So how do you find divisions? You just say nabla, which you know how to express in each coordinate system. Then dot product the vector v. Then, if you remember very well, I said divisions doesn't have an arrow, so divisions gives us a scalar. Then the dot product, uh, I don't know. I think Mechanique du Poids they'll teach you about the dot product, and I'm sure you are familiar with the dot product. The dot product of two vectors is a scalar. So with gradient, what do you say? Nabla f. Then with divisions, it's very easy. If you have got nabla, it's very easy to remember. Nabla dot product, uh, maybe the vector v, because it's a vector. Okay. So, for example, they asked you to find the divisions in the Cartesian coordinate system. Very easy. So you say divisions of the vector v, whatever vector that you have, is equal to nabla dot v. There's a difference between a dot in between and just multiplying, like the one for gradient. Okay, so now how do you do it? You have to know what is nabla. This is why I told you to memorize. If you can't understand, memorize nabla in each coordinate systems. So in the Cartesian coordinate system, if you are dealing with a Cartesian coordinate system, it's very simple. Then you put a dot, then the vector v. Then suppose okay, the vector v has got also have got different components. Okay, this is how you write, because it's a vector, you can write it as a matrix. So how do you find the dot product? The dot product is one of the easiest things to find. The dot product is one of the easiest things to find. You just multiply. No, the dot product won't give you a vector. So when you write something as a matrix, you're telling me that it's a vector. So it will give me a what? A scalar. So it will just give me a certain value here, which will no longer be a vector. The dot product is one of the easiest things to find. You just multiply this, then add it to the product of this, then add it to the product of this. The dot product is one of the easiest mathematical tool to deal with. So you just say partial derivative with respect to x, then multiply by vx. So which means you have to find the partial derivative with respect to vx, or vx with respect to x. Then you add, you say plus, then you multiply these two. Partial derivative with respect to y or vy. Then you also add, you multiply these two. Very simple. So notice that all you have here is magnitude. You don't have direction. Therefore, you've converted the vector v into a scalar. And the dot product the divisions mathematically converts a vector. So you say nabla, the same nabla that I've taught you, but you put a point, and the dot product you find it by what I've just have explained. You multiply this plus the product plus the product. Very simple, straightforward. Then whatever you're going to have is not going to be a vector. So don't put it in a matrix. Whatever you put in a matrix form is not a vector. Is a vector. You are telling me that you've got three components in these directions, but this one is a vector, is a scalar. So the dot product, or it's also called the scalar product because it gives us um, the scalar. I don't know if you've studied any mechanics before. He's supposed to teach you about the scalar product or the dot product. So you just have to know divisions, a dot. Then the last thing is the rotational. How do you find the rotational? Because of time, rotational of a vector. So as you can see, the question that you need to ask yourself, the overall uh, 2 has got an arrow on top. So this is a vector. So it can be written as a matrix. It won't be a scale. So rotational, how you find rotational, you just say nabla. You always start. Notice that these parameters, I explained to you what these parameters mean in physics, and now I'm explaining to you how to work with them in mathematics. So you always start with nabla, but for rotational you use this cross for the times symbol, or but the standard is this one. Then your vector here. So nabla vectorial v. I don't know if you have. We also talked. I think yes, we learned the vector products together actually. So here you're going to carry out the vector product in a way that you should watch my other video in a way that you do the vector product. So how many minutes am I remaining with? So I've showed you how to carry out the vector product. Now I'm going to show you the rotational, then we'll call it a day. Then next time, inshallah, we'll look at exercises on rotation, divisions, and things like that. That's what we're going to start from. So people who didn't attend, tell them to watch this video. So rotational of a vector, okay? So we said by definition, mathematically, nabla. This is why nabla is a very important operator in mathematics. It will help you. You just have to know vectorial or a cross in some books, the vector. So the nabla differs according to the coordinate system, as we've seen the entire period of this class. So del over del x, del over del y, del over del z. This is nabla. This is nabla in the cylindrical coordinate system. Oh, in the Cartesian coordinate system. Sorry. So vectorial. Then let's say a vector is composed because it's a vector, so it will be written as a matrix and in different components. Okay. So now, how do you carry out the vector product? I told you that the vector product is easy to find. You cancel out this part, then you carry out the determinant. There are some people who found there were some people, I don't know if they, I don't know. So this is how you carry out the vector product. You cancel the first element. If you of course the vector product will always give you a vector. Okay. The first component, how do you do it? You cancel the first part, then you do this. You carry out the determinant of the remaining matrix. So how do you find the determinant? You multiply this multiplied by this. So you're going to have del over del y multiplied by vz. Then you subtract from del over del z multiplied by vy as the first component. Then in a similar way, if you want to find the second component, you cancel out the second part. So you're going to have this as the remaining matrix. It's a 2 by 2 matrix. So how do you do it? So you carry out a product like this. Okay, so that is you find the determinant. So you're going to, but for the second part, please, for the second part, you put negative, then you do the determinant. So the determinant is very simple. You don't have to do a determinant. This is how you work with the vector product. Okay, explaining to you in a way that they understand, because with the books they will just give you this, they won't tell you how they were doing this. So now I'm teaching you how you can remember. This is just how I remember. So I'll cancel out the last part. Don't forget the negative here. It's plus, negative, plus. Someone wants to join now. Then you will remain with this. So you find that the remaining, you carry the determinant here. It's plus, so you don't need to add the negative. So you're going to have del over del x v y minus del over del y v x. So this is how you find. Therefore, if you want, you have the formula for rotation will be rotation of a vector v will be written as how many minutes? How many minutes? Okay, 5 minutes. So you find with rotation, you find this complex thing. It's just by knowing nabla vector v and knowing how to carry out the vector product. We learned how to carry out the vector product in our first lesson. So when you count the vector product and apply everything, you find that this is the formula in the bus Cartesian. So the only thing that will be changing depending on the system is the um, um, is the nabla. The nabla operator is the only thing that will change here. The vector will be the same. The formula will be the same. Okay, okay. So which is equal to this. Okay. So in summary, just to summarize because we don't have time. So gradient converts a scalar f into, so you're going to have nabla f into a vector, and this is a vector, which means it should have a magnitude and direction. Then divisions of a vector converts a vector, that's the opposite of this, converts a vector into, so this will be nabla dot, so you have to know how to carry out the dot product. Okay, this is a scalar. Then rotational of a vector is nabla vectored v. So this gives us a vector. This is a vector. So all you need to know is how to express nabla in each coordinate system. So if you don't understand, at least memorize and know how to apply, because the questions that I'm going to ask you is how to apply them. I'll just ask you find the gradient of f in the Cartesian coordinate system. Even in your exams, even in your schools, you'll find questions like this. So all you need to know is know or memorize the number notation and know how to apply it, the application part, uh, and also know how to interpret uh, 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 these notations. So this is why the number operator is very important. Know it and memorize it at all cost. So thank you very much.